All right, welcome to the week 7, I believe it is, Math 2413 review. In this one, we'll again just go over the chain rule really quickly at the beginning because it is so important, and then we'll talk about implicit differentiation, which I believe we maybe touched on briefly last week. Actually, no, I don't think so. We'll also go over derivatives of inverse trig functions, derivatives of logs, and also get into some log differentiation. So a lot to cover today. Should be fun. All right. So first up, we'll just do a brief review of the chain rule. Chain rule. And if we want the formal definition, that says if we're taking the derivative with respect to x of f of g of x, well then we take the derivative of the outside, and then we multiply by the derivative of the inside. Just like unwrapping a lollipop, you always work your way from the outside in. Derivative of the outside times the derivative of the inside. So for example, let's say we had h of x is equal to the square root of the natural log of 4x squared plus 1 squared, like that. Well, we want to work our way from the outside in, but first there is one trick that I'm going to do, and that is I'm going to use a log rule to get rid of this squared right here. So h is really just equal to 2 times the natural log of 4x squared plus 1. And I did that so that I wouldn't have to use the chain rule on it to get rid of this squared up here. It's a lot simpler to just turn it into a constant while I can.
And you have to do ln on the h of x, right? Too?
I am not doing log differentiation here.
Okay.
Right now. All I'm doing is I started with my original h of x function, and it just happened to have a natural log in it.
Oh, okay. Yes, sir.
Yep. Good question, though. All right. So now I'm ready to start taking the derivative. I always want to work my way from the outside in. My outermost function is that square root. So if I'm taking the derivative of square root, I can think of that as something to the 1/2. Its derivative is 1/2 times u to the minus 1/2 times the derivative of the inside. So what I'm going to do is I'm going to end up with 1/2 multiplied by 1 divided by the square root of, we just leave the inside alone, and then we multiply it all by the derivative of the inside, which is 2 natural log of 4x squared plus 1. And this is h prime of x. Well, now, solving the derivative of 2 natural log of 4x squared plus 1, my 2 is a constant. I'm just going to pull that out front. My outermost function now is natural log. We haven't actually touched the derivatives of natural log in this review session yet, which is why I'm doing this in the example, but you should have learned it in class. So this will just be a preview for later on in this review. The derivative of natural log is going to be 1 divided by the inside multiplied by the derivative of the inside. And of course, we would still have our 2 there. And of course, we know the derivative of 4x squared plus 1. It is just 8x. So then this derivative becomes 2 times 8x divided by 4x squared plus 1, which is 16x over 4x squared plus 1. And then this derivative, we plug right back in here. And as a final answer, we would get h prime of x is equal to 1/2 multiplied by 1 over the square root of 2 natural log of 4x squared plus 1 times 16x over 4x squared plus 1. And if we really wanted to simplify, we could cancel this 1/2 out front with the 16 out here. And this would give us h prime of x is equal to 8x divided by the square root of 2 natural log of 4x squared plus 1 multiplied by 4x squared plus 1. Alrighty, any questions? Got one. Using log rules, couldn't I bring the square root as a 1/2 in front of ln? So this is actually a really good question because it's something that a lot of students do get confused on. The answer is actually no. You're saying, well, if we have the square root of a natural log of something, can we say it's equal to 1/2 times the natural log of something? And we want to know, is this true? The answer is no. These are not the same. The situation in which we could say 1/2 natural log of u is if we had the natural log of the square root of u. This is equal to natural log of u to the 1/2, which is 1/2 natural log of u. The square root of the natural log of u is equal to natural log of u to the 1/2. So basically, your exponent has to be attached only to the inside part in order for you to use a log rule. So in this case, we're good. In this case, it's outside of our parentheses. We can't use it. Does that make sense? Yeah. But very important distinction there. Good question. We can't use our log rule.
What if you put the half after the ln? So like it's ln to the power of a half to u, because isn't that how it's normally written?
Sorry, could you repeat that?
So like you have ln to the power of a half, and then your u.
Like this?
Which one? I'm sorry.
Are you saying like this?
Oh yes, sir. Yes, sir.
I don't think I've ever seen this notation with natural log specifically. Sometimes you might see it with sine and cosine in your trig functions.
Yes, sir.
Again, in this case, this is, I would say it's probably like this. So these are the same, so you wouldn't be able to use the log.
So that 1/2 doesn't distribute to both the u and the ln, it only distributes to the ln.
Well, you're kind of trying to treat so you're saying distributing the 1/2 as an exponent.
Always do that, I see.
You're almost treating your ln as a separate variable,
Sure.
when really the natural log of u is one cohesive function.
Sure.
So you would only distribute if they're two separate things. But in this case, natural log of u is just one thing.
Sure.
Yeah. Good question, though. Any other questions for this example? Nope. All right. In that case, it's practice problem time. These ones shouldn't be as devilish as the ones I gave you last week. I just have to wait for OneNote to finish glitching on me. There we go. All right. Practice. This one gets an exclamation point. All right. And yes, these problems are maybe just a little bit mean, but not that mean. I'll give you a couple of minutes to work on those.
First one's pretty easy, right?
It's not too bad. I could make it harder if you wanted.
No, I just wanted to make sure I wasn't underthinking it. think so. I think. So that's my answer for the second one. That's my answer for the first. C squared, this squared. Oh, what is secant squared?
There we go. Yeah. All right. Let's go ahead and go over these. So the first one, fairly straightforward. We always start with our outside. Our outside function in this case is sine. The derivative of sine is cosine. We leave the inside alone. And then we multiply by the derivative of the inside. The derivative of e to the x plus 1 is e to the x plus 1. In this case, the derivative of x plus 1 is just 1, so we could think about multiplying by 1 here, but it doesn't make a difference in our final answer, so we'll just leave it out. For the second one, again, we always start with our outside function. Again, it's sine. Derivative of sine is cosine. We leave the inside alone. Then we multiply by the derivative of the inside. The inside now is cosine of tangent. We start with our outermost function. In this case, because we're only looking at cosine of tangent, the outermost part would be cosine. Derivative of cosine is negative sine. Leave the inside alone. Then we again multiply by the derivative of our inside function. Our inside function is tangent. Derivative of tangent is secant squared. So then our final answer would be equal to negative cosine of tangent x times sine of tangent of x times secant squared of x.
If I asked you to draw out the entire unit circle, what's the smallest you could go to? Or could you just go to infinity?
Draw. What do you mean draw out the entire unit circle?
Like the coordinates, like all of it.
I mean, you could. So if I started drawing the unit circle, this is a good question actually, because it usually the unit circle, the important values you need to memorize are. This is definitely a bit of a tangent, but the important values, we've got 0, pi over 2, pi, 3 pi over 2. But then there are really 3 main points you hit in each quadrant. And roughly they are, well, my lines are probably not exact, but they occur at pi over 6, pi over 4, and pi over 3. But we know a lot of trig identities. So we know on the unit circle the values of sine and cosine at these points. So for example, sine of pi over 6 is equal to 1/2. There are probably clever ways, though, that we can find our other values on our unit circle. For instance, there are a whole lot of trig identities. So we could always find a double angle. So we could find sine of 2 times an angle as 2 sine theta cosine theta. But there are even better identities that we could use. We could use some in different. Actually, I'm just going to pull up a table of identities here. That's probably the fastest way. Trig identities, perfect. Images. This one looks good. Let's open it. And for anyone online, sorry about the mild distraction. But here we go. So here we have a bunch of trig identities. I think the ones we're probably most interested in might be the sum and difference ones, and possibly even the half-angle identities. So for example, we know the cosine of pi over 6. If we let pi over 6 equal to 2 theta, then we could find sine squared of pi over 12, because cosine of pi over 6 is root 3 over 2, so we would have sine squared of pi over 12 is equal to 1 minus root 3 over 2 all over 2. And from there we could find sine of pi over 12. And we could then use sine of pi over 12 to find cosine of pi over 12, which we could then use again to find sine of pi over 24, and so on and so forth. So there's really infinitely many values we could find on the unit circle. Whether all of them are useful or easy to find at all is another matter. But we can find as many values on the unit circle as we want. I guess the weird thing to note, though, is you won't necessarily be able to get from any of your unit circle values directly to any value that, or any sign value. So what do I mean by this? This is a wee bit of a tangent, for sure.
Do you mean like a y value because it's a strange fraction?
No, I mean like, so with your trig functions, they take in an angle, right? All of our unit circle angles are currently based on pi. Now, it would be really, really hard to get from one of our angles based on pi to just an angle like 1 radian instead of like pi radians, just 1. And the reason being is because we'd probably need to somehow divide some of our angles we have currently. So like say pi over 6 over pi over 3. But we don't have any trig identities that would allow us to cancel those pi's because there's no division identities. So we could get a lot of values based on just our unit circle values, but not all the values. And usually it's more trouble than it's worth. It's just that pi over 6, pi over 3, and pi over 4, pi over 2, and those ones just come up so often that the unit circle is helpful. All right, that was a bit of a tangent. Sorry about that, but it was fun. Back to the actual lesson. Let me share OneNote again. All right, perfect. Here we go. All right, now we'll talk about implicit differentiation. Implicit differentiation. All right, and you've been doing some of this in class. And the reason implicit differentiation is useful is because it lets us take the derivative of functions where we don't have y equals. So what if we don't have y equals? Y is specifically equal to a function of x. Well, we can use what's called implicit differentiation to take the derivative of functions such as x squared plus y squared is equal to 1. In this case, there's really no way we can just turn this into a single simple y equals equation. We could move the x over and then take the square root of each side, but then you're having like plus or minus 1 minus x squared, and that's not a pretty function to look at, when really this is just something simple. It's just a circle. So implicit differentiation, how it works, you take the derivative as you would using all your normal derivative rules, except your derivative of x, as usual, is just 1, but then your derivative of y is dy over dx. So what do I mean by this? Let's take the x squared plus y squared equation. If I'm taking the derivative, well, x is a variable, I take the derivative. Derivative of x squared is 2x. Next, I come across y squared. Y is a variable, so I need to take the derivative using all of my normal derivative rules, in this case the power rule, 2 times y, but now the derivative of y is dy over dx. And then the derivative of 1 is just 0. So I guess one thing to note is we have 2y dy dx because of the chain rule. You can think of taking the derivative of y squared as first, you handle the squared part using the power rule. You bring the 2, decrease the power by 1, but then by the chain rule, you have to multiply by the derivative of y. And the derivative of y is dy dx by our rules of implicit differentiation. Make sense?
Y cubed would be 3y dy over dx, right?
Sorry?
3y would be dy over dx, right? Hold on, I'm sorry. So y cubed, the derivative of that would be just 3y dy over dy over dx, right?
So you're saying your claim is that the derivative of y cubed is 3y times dy over dx?
Yes.
So I'm going to disagree.
Okay. So I wasn't sure if I was smooth brain or not.
Do you
It's
know?
3y squared.
Right, you would need to keep your squared up there because it's just the power rule.
Okay.
Just like normal derivatives, it's just that when you take the derivative of a y, you have to write a dy dx. Good clarification, though. All right. From here, we actually want to isolate dy over dx. So to do this, you move everything that does not have a dy dx attached to it to the other side, and then just divide both sides by everything except dy dx. So to cancel the 2y on this side, I just divide both sides by 2y. And this gives me negative x over y. That would be my derivative. Fun stuff, huh? All right, let's do a slightly more complicated example because circle's pretty easy. Let's do 4x squared y is equal to the sine of x plus y. Well, to take the derivative of my left side, I have one function being multiplied by another function, so I need to use my product rule. Derivative of 4x squared is 8x, and I leave the y alone. Then I add 4x squared multiplied by the derivative of y. Derivative of y is dy dx. That's the derivative of my left-hand side. For the right-hand side, the derivative of sine is cosine. I leave the inside alone, and then I multiply by the derivative of the inside. Derivative of x is just 1. Derivative of y is dy dx. Now, my next step, so my first step was to differentiate. My next step is I'm actually going to distribute cosine of x plus y to 1 and to dy dx. And the reason being is because I want to move everything with just a dy dx on it to one side and everything else to the other. All right. I did not distribute at all. All right, so we got cosine of x plus y times 1 plus dy dx times cosine of x plus y. Now I'm going to move everything with the dy dx on it to one side and everything else to the other. So I have 4x squared dy dx minus dy dx times cosine of x plus y is equal to cosine of x plus y minus 8xy. All right, second step. Put all dy dx terms on one side. And the reason I do this is because now that all of my dy dx terms are on one side, I can easily factor out dy dx. And that would be my third step. And now it's really easy to get dy dx by itself. I can just divide by everything that's not dy dx on this side. So in this case, I would divide both sides by 4x squared minus cosine xy, or cosine x plus y. And I get that dy over dx is equal to cosine of x plus y minus 8xy all over 4x squared minus cosine of x plus y. Perfect. And 4 divide. Any questions? All right. In that case, let's go ahead and do some practice problems. How are we on time? Okay, we're good on time. Practice. Perfect. Find dy over dx. And just one right now. There we go. I'll give you guys a few minutes to work on that.
Do you think of an outcome today? Because I plugged into like 2 outlets. This is the second one that just don't work. Okay.
That's
Let's see if anyone works.
yeah. Well, we know if this one works.
Oh, this one over here.
Well, that one with that's plugged into. There's one small next to it.
So I'm not frying my charger every time I plug into it.
Yeah.
Okay, that one works.
Love to hear it.
What?
You're picking it.
Yeah, I'm very lucky. I think I'm just weird like that because I'm one of the few people that prefers in-person stuff that I've met.
It's in person for not.
Yeah, that's exactly how I am.
Yeah.
And then also, if you're online, then teachers ignore your questions that you type in chat.
Yeah. I didn't know this or my this. Okay. So
Is that an equal sign between the tangent and the y squared?
yeah. All right, online people, how are we doing? Good, you got an answer? All right, let's go over it real quick then. So first off, derivative of the left-hand side, pretty straightforward. Derivative of x squared is 2x. Derivative of y squared is 2y. We took the derivative of y, so I put in a dy dx. Derivative of the right-hand side, again, not bad. We know the derivative of tangent. In this case, we're using the chain rule, so we work our way from the outside in. Derivative of tangent is secant squared. We leave the inside alone. And then we multiply by the derivative of the inside. Now the derivative of xy, we'll need to use a product rule here. So derivative of x is 1 multiplied by y plus x times the derivative of y is uy dx. That's our derivative, but now we need to get dy dx by itself. So again, I'm going to distribute secant squared of xy. And then I have plus x secant squared of xy. What am I writing? Of xy multiplied by dy dx. Now again, I'm going to put anything with the dy dx attached to it on one side and everything else on the other side. I'm going to put everything with the dy dx on it on the right-hand side, so I have 2x minus y secant squared of xy is equal to x secant squared of xy times dy dx minus 2y dy dx. Again, I'll factor out dy dx, and that gets 2x minus y secant squared of xy is equal to dy over dx times x secant squared of xy minus 2y. And finally, my last step again is just going to be dividing everything that's not dy over dx out to the other side. So I get that dy dx is equal to 2x minus y secant squared of xy all over x secant squared of xy minus 2y. All right. Another answer you might have gotten, depending on which order you did things in, you could have gotten y secant squared of xy minus 2x over 2y minus x secant squared of xy.
Sorry for a second.
So these are the same thing. It's just that if we take this second result and multiply by -1 over -1, we'll get the first thing. So it really comes down to which side did you decide to put your dy dx's on, whether or not you got this one or this one, but they're the same answer. So just a note if you got something slightly different than what I got. In line 2, do we have to distribute secant squared of xy? You treated the multiple as a single term and subtracted it. So you're saying, why did we go from here to here? So the idea is, let's say you don't distribute and just subtract. Then you would have 2y times dy over dx minus secant squared of xy times y plus x dy dx is equal to -2x. If you just subtract your secant squared xy times y plus x dy dx over, and also move the 2x over to the other side since it doesn't have a dy dx. Well, the problem with this approach is that we can't immediately factor our dy dx's out. Here we have a dy dx in our first term and in our third term, but we will have a term secant squared xy times y that doesn't have a dy dx attached. So that means that we can't actually factor out a dy dx. And that's a problem because if we can't factor out a dy dx, then we can't divide everything else over, and it's really hard to isolate dy dx. So for example, from here, you could distribute now and then just move secant squared xy times y back over. Yeah, factoring right here is not allowed. So that is one thing you need to be careful of. But good question. Good question. All right, we good on this one? Perfect. In that case, let's move on. Time for some more derivative rules. In this case, we're going to be talking about derivatives of inverse trig functions. All right. Now I know how much you guys all love trig, so I'll be sure to throw in a good amount of trig for you. First off, though, let's also, one thing to note, you'll sometimes see inverse trig functions written like this. You'll also sometimes see them written like this. I will exclusively use this notation because this notation gets me confused with, well, is this equal to 1 over sine of x? And the answer is these are different things. So this notation always confuses me, so I will avoid it whenever possible. I will always use the arc sine. All right. But just to be aware, sometimes you will see sine to the -1, which means sine inverse arc sine. So just be aware of that. All right, derivative of arc sine of u is equal to 1 over square root 1 minus u squared times the derivative of u. You might also see it written as just du over square root 1 minus u squared, and that's the exact same thing. Next, we would have arc cosine, and this is just like arc sine except negative. Then we also have arc tangent, and this one is actually du over 1 plus u squared. So this one's a bit different, but still fun. Then we would have arc cosecant of u, and this is negative du over u times the square root of u squared minus 1. Next we have arc secant of u, and this is arc cosecant, but we dropped the negative, so du over u times the square root of u squared minus 1. And lastly, we have arc cotangent. And this one is just like negative arc tangent. All right, so there's your 6 inverse trig functions and their derivatives. One helpful way to remember which ones have negatives is it's all the ones with C's. These all have all the negatives, the other ones do not. So that's if you're having trouble remembering all the negatives. But if not, you can forget that fact. All right. So I think you guys are probably fairly familiar with using inverse trig functions so far, or at least you've gone over it in class. So I'm not going to really do example problems for these. Instead, I'll just put them in the practice problems so you'll still see them worked out later on. Anyway, one quick practice problem though, that's also going to be with implicit differentiation. Go ahead and try to find the derivative of arc sine of y plus 3 equals to xy. And I'll give you a couple minutes to work on that.
Wait, you're in ACS class? What do you have to do that for if you're a math major?
All right, let's go over this problem real quick. So again, implicit differentiation. Again, I have to wait for OneNote to finish lagging on me. There we go, and there we go, perfect. All right, derivative of arc sine. If we look back at our handy dandy chart, derivative of arc sine is du over square root 1 minus u squared. Derivative of y plus 3 is just dy dx. So then we'd have divided by the square root of 1 minus y plus 3 squared. Derivative of the right-hand side, well, we could take derivative of x as 1 multiplied by y plus x times derivative of y. All right, so then we get dy dx times 1 over square root 1 minus y plus 3 squared minus x dy dx is equal to y. So dy over dx times 1 over square root 1 minus y plus 3 squared minus x is equal to y. Actually, I am going to rewrite this x as x times the square root of 1 minus y plus 3 squared divided by the square root of 1 minus y plus 3 squared, just so I can combine my fractions. Because then it makes it a bit easier to multiply everything over. I won't have fractions within fractions. I'll just multiply by the square root of 1 minus y plus 3 squared divided by 1 minus x squared root of 1 minus y plus 3 squared on each side. And there you have it. There is our answer. Any questions?
So for your square root, if you took that to the power of a half, I know it doesn't matter for this problem, but in general, if you did that, could you never mind. I asked this question earlier. I always struggle. Never mind.
Were you going to try and cancel with the y plus 3 squared?
I was going to try to distribute it into the parentheses, because that's just the way my mind works, but you can't do that with the power at all. Like even with squared, you can't do that.
Well, sometimes you can. For example, if we were looking at this, this is actually the same as
Wouldn't the half only go on the denominator?
well, that's the thing. Technically, it goes to both. You're right in that we only need it applied to the denominator. So it actually does get applied to both the numerator and the denominator. But then the square root of 1 is just 1.
Okay. Okay.
So when it's outside the parentheses like here, it does get applied to both the numerator and the denominator. In the world. It's just that in this case, the square root of 1 is just 1. So.
So it's more of a notation thing than. Because it would be correct even if you only applied it, like even if you only put the denominator to the half, it would still be correct.
Yeah.
So this is more of a notation thing.
Yeah, this is, yeah. It's almost like just a special case where because we have the square root of 1 as 1, we can just put it outside the parentheses around the whole thing. We could also do it just around the bottom. that. So yeah, any of these are all the same. Good question. Isn't there a shortcut where you switch the denominator with the other side of the equation? So let's see, I think that might be what I actually did here. So let's see. You'll notice that I'm just going to use highlighter because handy dandy technology. This part came from the denominator right here, and then the denominator right here came from the numerator right here. So yeah, I guess that is the shortcut. I always think about it in terms of multiplying by the denominator and then dividing by the numerator, just because that's how my brain works. You can also think of it in terms of your shortcut if you want, but yes, exactly right. Oh, you mean after the first step? Like a over, okay. So you're saying take my dy over dx over root 1 minus y plus 3 squared is equal to y plus x dy dx, and then rewrite it by switching it to be dy over dx over y plus x dy over dx is equal to root 1 minus y plus 3 squared. Okay, so this is correct mathematically, because it's just like multiplying square root 1 minus y plus 3 squared over and then dividing by y plus x times dy dx. The primary issue here is that it doesn't really help us at all, because we still can't factor out dy dx, because specifically dy dx is missing from this term right here. So we can't factor dy dx out of the bottom, so we can't factor it out of our whole fraction. So while this is correct mathematically, it's not very helpful, if that makes sense. Yep. If it were just the x dy dx, then it might be another matter. But again, we actually don't want our dy dx's to cancel, because then we don't have any dy dx's, and that's a problem because we just took the derivative.
Well, couldn't you just technically pull them out and have 1 over y, or well, just x?
Well, if we had, yeah.
Instead of canceling?
Well, then you would have to pull out a dy dx from the top and a dy dx from the bottom. So you would still have dy dx over dy dx. So.
Oh, so you can't just pull one out from the numerator and denominator and have it be one solid term of itself? Okay.
Yeah. So if your dy dx's all cancel out, that is a problem. It means you did something wrong. So just a heads up with that. All right. Cool. Any questions with this problem, though? All right. Let's move on. You get even more log rules now. Well, even more differentiation rules. These ones apply to logarithms, which you've seen a bit lately, I'm sure, because I've been putting them in my examples because I keep forgetting you haven't learned them yet. But no longer. I'll be able to torment you with logarithms for a long time now. As long as one note, there we go. Perfect. So let's talk about derivatives of logarithms. First off, we have our natural log. And the derivative of the natural log of u is so gorgeous. It is du over u. Fantastic. You might also see it written 1 over u times du. Also a nice way of putting it. If you have the derivative of a logarithm that is not natural log, sorry, I shouldn't have written natural log. So we're going to say log base a. So it could be, for example, log base 10, log base 2, log base whatever you want that is an e, or even e, in fact. This is equivalent to 1 over u multiplied by the natural log of a, your base, times the derivative of u, which is again just du, over u times natural log of a. All right.
Can you show us why that is, or is that like?
Can I show you why it is?
Yeah, why the derivative of each of those is what it is?
It comes from your. All right. So there is a somewhat poorly known formula or law, and it's basically. Have you heard of the change of log base rule? Probably. They maybe touch on it once or twice. I always forget it, but luckily I can just look it up really quick. Perfect. So our change of log base formula says that the log base a of b is equal to log base whatever we want, c of, I believe it's b, divided by log base c of a. So this is your change of log base formula. And in order to get our derivative rule, what we can say is that we can just let c be equal to our natural constant e. In that case, we get that log base a of b, well, log base e is just the natural log. So is the natural log of b divided by the natural log of a. Well, the natural log of a, since a is a constant, the natural log of a is just a constant. So if we wanted to take the derivative of log base a b, we can just pull our constant out. And then the natural log of b we know to be the derivative of b, I'll denote it b prime over b. And this gets us exactly what we're looking for. We could actually probably better to represent this as db just so we're consistent with our notation. And this gives us exactly this formula right here. Make sense?
But don't you have to know that formula to apply it to that equation?
So you're saying, don't I have to know this change of log base formula?
No, the 1 over the du over u. Don't you already have to know that to apply that over here?
Well, to apply that to, well, we know what the derivative of natural log is. So the difference is, here I have a log of any base. Here I just have the derivative of natural log.
Yes, sir.
And if you really wanted to, you could probably derive the derivative of natural log using your definition of a derivative.
Oh, no.
But that does not seem very appealing to you, so we'll skip it. Probably because I don't know if I could just off the top of my head. That would need a bit of preparation, but basically, here's your change of log base formula. It's how we get the second equation from our first. You can write it down if you want. It might come up very occasionally, but hardly ever, in my experience at any rate. All right, so these are your derivatives of logs. I'll go ahead and put them in a box just so everyone knows where they are. And let's do a quick example. Let's say we wanted to take the derivative of log base 2 of x sine x. Well, again, I'm going to use the chain rule. I start with my outside and work in. My outside function is log base 2. I know my derivative of log base 2 because I have my general form for it. It would be 1 divided by the inside, x sine of x, And then I would also have to have in my denominator the natural log of my base, so the natural log of 2. And then I would multiply by the derivative of the inside. So the derivative of x sine x is sine of x plus x cosine of x using the product rule. That would be my derivative, f prime of x. Any questions? All right. In that case, it is time for some more practice problems. And I'm going to keep making you do implicit differentiation. Because I am rude like that. Second one is just normal though.
Is there a pencil sharpener in your mind?
It should be, but I don't know if it is.
Okay. Thank you.
I can probably pull out another pencil. There's some.
No, you don't have to do that. You're fine. I'm good enough for now.
I
I
did
just
not
was
touch
curious.
these since high school. Like,
That's probably this pencil too for me. Sure. Thank you. Yeah, thank you so much. So you just use the same bag since all of high school, and they just had those pencils. sitting
Actually, they
there?
might have come from freshman year.
Oh, here.
Yeah,
Okay.
but
Are you a junior or a sophomore?
junior.
Yes, sir.
Yeah, so it's I don't know why I have them. I think it's for Scantron supposedly, but I don't ever use Scantrons. I think I had one class. Maybe two.
Did you get them out of the vending machine, or did you get them at the?
Just the bookstore.
Okay.
Yeah, no, it's sad.
I just. The fact that they make you buy your own Scantrons, they can't like just provide you one to print off on your own sheet of paper.
They used to like just give them up for free at some places, but then it stopped.
College is a business thing. It really. I didn't hear you say that though.
Right.
It's a peer too.
It's loads of fun. We love learning.
They love more money more than anything else though.
I don't know. Math is fun. For A, would I recommend using the multiplication log rule? I actually never considered that. I think you wrote your rule wrong, but you're saying, what if we rewrote natural log of x plus y as the natural log of x? Well, you have it backwards. This is not your rule. This is not true at all. Your rule, remember, is the natural log of x plus the natural log of y is equal to the natural log of xy. Would I recommend doing this? Well, it doesn't apply in this case, so probably not. And in general, it's usually easier to take the derivative when there's addition rather than taking the derivative when there's multiplication. So one thing you might consider is switching is if you had something like this going to this. But in general, it's probably not a great idea to go from this to this, just because it'll probably make you use the product rule. Yeah, don't worry about it. Good thinking. It always is good to think about your log rules that you can use, but in this case, they don't apply. And again, taking the derivative using the product rule is harder than not using the product rule, so. All right, let's go over part A because I do want to get to log differentiation because that stuff is cool. All right, derivative of the left-hand side here. Well, derivative of natural log is 1 divided by the inside multiplied by the derivative of the inside. Derivative of log base 10 of x, well, here we can just use our rule that we wrote down earlier. We can see that it would be derivative of x is 1 divided by the natural log of 10 multiplied by x. Perfect. Now we need to isolate dy over dx. In this case, I'm actually going to multiply both sides by x plus y first. So then I have 1 plus dy over dx is equal to x plus y over x times the natural log of 10. So then dy over dx is equal to x plus y over x times the natural log of 10 minus 1. And you could turn this all into one fraction if you wanted to. I do not want to, though, so I'm not going to. All right, part B. Part B, we actually don't need to use implicit differentiation. I figured the problem was probably good enough without throwing in a few more y's. So derivative of y is dy over dx. And then derivative of arctangent, well, again, we need to use the chain rule because we have lots of things stacked inside, so we start with the outside. Derivative of arctangent is going to be derivative of the inside divided by 1 plus whatever the inside is squared. And then the derivative of the natural log of x, well, we know that it's just 1 over x. Now, I don't like having fractions in fractions, so I'm going to rewrite this as 1 over x multiplied by 1 over 1 plus the natural log of x squared. You can think of this as being a fraction over a fraction. And one of our rules for fractions is if we have a fraction over a fraction, we can think of that as the product of two fractions. You take a over b, and then you multiply by, flip the denominator. And this is really the way I think about fractions and fractions, because dividing fractions is hard. So I like to avoid it and turn it into multiplication. So then, as a final answer, we get 1 over x times 1 plus the natural log of x squared. All right. Question. Can I bring my 2 down in my natural log of x squared? Can I use that log rule to bring the 2 down? No. Good. We cannot. The squared is not just the x on the inside of the natural log, it's to all of it. Because it's to all of it, including the natural log, we can't bring it out front. So this would be our final answer.
Couldn't you technically also distribute your x if you wanted to?
Yeah, I could distribute my x.
But it's clear like that, though.
Yeah, I mean, it doesn't actually really make much of a difference as to how clean it is, so this is fine.
Yes,
Good question, though. All right. Now it is, okay, we've got maybe 15-ish minutes left. So we can talk about some log differentiation. Now this stuff is cool. I believe you covered it in lecture yesterday. But the main idea behind this is sometimes our log properties are really, really useful. So sometimes it can be helpful. Sometimes it can be helpful to take the log of each side. So for example, let's say we had, this is the classic log differentiation problem, the function y is equal to x to the power of x. Well, this doesn't exactly fit any of our differentiation rules, right? We know how to take the derivative of x to a constant power. We know how to take the derivative of a constant to the power of x. We don't know how to do it when they're both in there. But if we take the natural log of each side, well, in this case, our power rule for logs does apply. We can bring our x as an exponent out front as a coefficient. Well, suddenly, we know how to take the derivative of x times the natural log of x. So I am going to use implicit differentiation to find the derivative of the natural log of y is equal to the natural log of x natural log x. Right. So taking the derivative, I would have 1 over y multiplied by the derivative of y, which is dy dx, is equal to, on the right-hand side, I use the product rule. Derivative of x is 1. Leave natural log of x alone, plus x times the derivative of natural log of x, which is 1 over x times 1. Now this right-hand side simplifies to the natural log of x plus 1. I need to multiply both sides by y in order to get dy dx by itself. So now I have dy dx. But right now, our original equation was just in terms of x. We suddenly threw in a y in there. Let's see if we can get rid of that y. Luckily, we know exactly what y is equal to. So all I'm going to do is I'm going to take the y right here out and replace it with the y right here, which I know is equal to x to the x. So this exact same. And that would be my final answer because, again, there are no more y's on the right-hand side, so we're good. Pretty cool stuff, huh? Any questions? For B, oh, sorry, I should look back at this. Sorry, I missed the question for part B. Why does the 1 over x go to the denominator, or on the numerator, you multiply the whole fraction by 1 over x? The 1 over x, that is also a perfectly valid way of doing it. I just used the du over 1 plus u squared version. I know we're skipping around a bit. So I just used this definition for arctangent. It looked like you went with the exact same definition of 1 plus u squared times du. And it really just changes how your thing would look. But that's kind of, you got the same thing, so. Yeah. All right. Any questions with this log differentiation example? Good? All right. Perfect. In that case, I'm going to give you a couple of practice problems. And of course, your job is just to find dy dx, of course, your derivative. First problem, y is equal to cosine of x to the x. And there's your second problem. I'll give you a few minutes to work through those. All right, let's go over these problems. We'll start with the first one. First one is, again, we don't know how to take derivative of cosine of x to the power of x. Taking the natural log of each side, we get which is equal to x times the natural log of cosine of x. So then 1 over y times dy over dx is equal to, here we have to use the product rule, gives us natural log of cosine of x, plus x divided by the cosine of x, times the derivative of cosine of x, which is negative sine of x. And the reason that is, first part, I took the derivative of x, left natural log of cosine of x alone. Second part, I have x times the derivative of natural log of cosine x. Derivative of natural log of cosine x is 1 divided by the inside, so 1 over cosine x, multiplied by the derivative of cosine x, so times negative sine x.
How come you didn't just take 1 over cosine x to the power of x for your derivative? How come you know that it's multiplication instead?
So you're saying, why didn't I do what?
So since the derivative of ln is 1 over what's on the inside, how come you didn't just take like 1 over what's on the inside and then multiply that by x?
So you're saying when I had natural log of cosine of x to the x, why didn't I just take the derivative here?
Yes, sir.
So let's try it and see what happens. Well, then I would have 1 over cosine of x to the x multiplied by the derivative of cosine of x to the x. Well, this is the same problem we started with. So that's the reason why, because we still don't know how to take the derivative of cosine of x to the x. That's why we decided.
You just put the x in front of it. I'm sorry. Yeah, you put the x in front of it because the ln, right?
Right, right. Because that's what our log rule allows us to do. Our log rule specifically, oh my goodness. Our log rule specifically allows us to take this x as an exponent and move it out front as a coefficient. And that's the real advantage of log differentiation. It lets us do things algebraically that we wouldn't normally be able to do without the log. Make sense?
Well, I'm so confused why you didn't take the x out. So you have ln of cosine over x, or yeah, cosine of x. So why didn't you put that over 1 and then take the derivative of x, so then have it multiplied by 1? Is I guess what I'm saying.
So
the part,
right.
The second line, but the last bit, take the derivative of that is, I guess, what I was actually asking.
Right here?
Yes, sir.
Well, this is what I took the derivative of. So I used the product rule.
Oh, okay. I'm sorry. Yeah.
Yep. All good. Ask for clarification. I just kind of merged the x times 1 over cosine of x right here. But good question. All right. Now I can multiply both sides by y. Plus x, or actually we have a negative since the negative sign, so minus x. And I have sine over cosine, so I'm just going to write that as tangent. And again, I can substitute my y back out. So for my final answer, I get dy over dx is equal to cosine of x to the x power multiplied by the natural log of cosine x minus x tangent of x. Perfect. Any questions with that one? All right. So for the second one, it's a bit different. Oh, question. Is it wrong if we leave y as y? It would be considered bad form because you're explicitly given a y equals equation here. So if you start with a y equals where y is equal to just x terms, you should probably give your answer as y equals just x terms, or dy dx equals just x terms, unless they explicitly say not to. If you start out with an implicit differentiation thing, where you have y's everywhere, then the whole reason you are allowed to leave y's in your answer is because you couldn't usually get a y equals equation to begin with. Yeah, so a good rule of thumb would just be to follow the form of the problem they gave you. If they gave you y equals, you should give out something equals just x. If they give you function with x and y mixed up everywhere, you can give out a function with x's and y's mixed everywhere.
So I also have a question. How can you multiply by y by everything instead of just multiplying by y at the end?
So like, why does my y go to all of this rather than just this part?
Yeah, instead of just getting tacked on the end. Yes, sir.
Right, so it's because I need to distribute it to everything. So whatever we do to one side of our equation, we have to do to the other, right? So I multiply this side by y. So I'm going to have to multiply this whole right-hand side by y. Because if I multiplied just by this part, well, then I wouldn't have multiplied y by this. So it wouldn't have been multiplying the whole side by y.
So if there was some sort of, if there was another term there, would you only multiply by y itself? Like, instead of multiplying everything by y, would you just multiply, just tack it on at the end like I was saying a while ago? Would that be different?
So are you saying like if there was another term, like plus something else?
It's on the left.
On the left.
Yes, sir.
So like, I don't know, like 4 plus or something?
Yes, sir.
Well then, in order to cancel the y, or to multiply by y, I would multiply everything on this side by y, and everything on this side by y. So the y would still get distributed to everything on this side. The y would also get distributed to everything on this side. So the y would cancel with this y here, but we would also have a 4y left over on this side.
Okay, that makes sense. Yes, sir.
Yeah. Yep. I have to pull everything out. Sine of x. I think it was just sine of x, and then dy dx. I hope that's rightish. We'll go with that. Okay, so that's the first problem. The second one is a bit different because we actually could solve this derivative without using log differentiation. The problem is we'd have to start by using the quotient rule, and then from there we'd have to use the product rule a couple of times as well. And that is just a lot of work to do. So let's see what happens if we do try to use log differentiation. I start by taking the natural log of each side. Well, there are other log rules other than just our log power rule. If you'll remember, we have this one, as well as our fraction rule. So we can actually break down natural log of e to the x times sine x divided by x times natural log of x into some parts. So this is actually how I can break down my function using my log rules. I have the natural log of e to the x times sine x divided by x divided by the natural log of x. So now that I have this, I can go ahead and take the derivative. In fact, before I take the derivative, the natural log of e to the x is just x. So then taking the derivative of x, I just get 1.
Shouldn't
Plus.
there be a plus sign between ln of x and then ln of x? Because of multiplication.
That is a good question. Really, I kind of did a couple of steps in one go. So you can think of it as being the natural log of e to the x times sine of x minus the natural log of x times natural log of x if I just apply my division rule first, right? And then I can apply my multiplication rule. but then I would distribute my negative to both of these. So that's why we have a negative right here.
Okay.
Let's see, where was I? Taking the derivative, right. So we took the derivative of x and got 1. The derivative of natural log of sine x is going to be 1 over the inside, so 1 over sine of x, times cosine of x, the derivative of sine x. Then we have minus 1 over x, minus 1 over the inside, 1 over natural log of x, times the derivative of natural log of x. The derivative of natural log of x is 1 over x. So 1 over y times dy dx is equal to 1 plus cosine over sine, it's cotangent, minus 1 over x, minus 1 over x natural log of x. So then, multiply both sides by y. And then we can substitute y back out. Any questions? When I broke up the x natural log of x using the log properties, you don't understand what I did since the x is in front. All right. Well, good question. Wouldn't there only be one? Okay. So your question is, how did I break up natural log of, or how did I break up x times the natural log of x? Basically, how did I get from right here down to the second part? Is that what your question is?
I think that's right.
All right, so let's address this. In this case, yeah, it's just our multiplication rule for logs. The natural log of a times b is the natural log of a plus the natural log of b. So I can take the natural log of x times the natural log of x. Here I let a be equal to x, so I could have that be natural log of x plus the natural log of whatever b is, natural log of x. Make sense? Yeah. All right, perfect. Any other questions?
So, sorry, I was a little behind the curve because I was a little lost, but so trying to figure out which step it was. Okay, so that 1 is from e to the x over e to the x, correct? On the second line, like the
Right here?
yeah.
So this one comes from, what I did here is I took my natural log of e to the x. Natural log of e to the x, I can actually simplify. Using one of my log rules, I can bring the x down as a coefficient. That gives us just natural log of e. But natural log of e is one of the values of natural log that we know. It's just 1, so x times 1 is just x. And then I took the derivative of x, and I got 1.
How come it's on the bottom right there? Is that supposed to be a division sign, or is that just you showing me?
Right here. Oh yeah, this is just me showing you.
Yes, sir. Okay.
Yeah.
Okay.
Not division right there. You're right. That makes sense.
Well, couldn't we also think about it in terms of like 1 over, or the derivative of ln of e to the x is 1 over e to the x, and then also taking the derivative of e to the x, which is e to the x, and that also gives you 1.
Yep,
Okay.
that's perfectly valid. All right, in that case, I'm going to go ahead and stop the recording. Thank you all for coming.